Good morning, students. Here is another very important topic from second PUC, physical chemistry, electrochemistry. So I have selected important multiple choice questions from other competitive examinations. So this will help you to prepare for all competitive exams you are going to write. So here the ideas used, the concepts used in electrochemistry are about electrolysis, products at the anode and cathode. Then we have calculation of quantity of electricity that is related to electric current and time. Then we have some laws known as Kohlrausch law, where it is applicable to limiting molar conductivity of electrolytes. Then we also have this law, that is a law that relates potential of a half cell with its standard potential, also the potential of a cell with the standard potential of a cell, known as the famous Nernst equation. So we also have questions on building up half cells or single electrodes, then coupling it with another half cell or single electrode, then building up a galvanic cell, calculation of the potential or the voltage of a galvanic cell. So EMF or voltage of galvanic cell can be calculated. So here we go for the consider the half cell reactions. Mn plus 2 electrons, Mn reduction. Look at this, addition of electrons or reduction. So there are two reactions of reduction. So inert values are their reduction potentials, standard reduction potentials. So I'll write it as SRP, standard reduction potential values. Inert for the reaction. The final reaction is given here, that is 3Mn2 plus Mn3 plus. Look at this. Here a part of it is reduced, another part is oxidized. We'll have to find the inert, the standard potential final reaction. So what you need to get from these two equations is the final equation. So looking at this algebra ನೋಡಿದಾಗ ಇಲ್ಲಿ ಏನು ಮಾಡಬಹುದು, ಇದನ್ನ into 2 ಮಾಡಿಕೊಂಡ್ರೆ this is second equation multiplied by 2, but be careful, inert value will not depend upon balancing the equation. Inert is an intensive property that will not depend on the number of moles. ಇದನ್ನ ಹಾಗೆ ಇಟ್ಕೋಬೇಕು. Second value into 2, first value ಎರಡನ್ನು add ಮಾಡಿದ್ರೆ second equation into 2, first equation ಎರಡು add ಮಾಡಿದ್ರೆ you get the final answer. Let us see the answer. Yes. The answer is minus 2.69 volts. And no, the reaction is not feasible because reaction potential is negative. Reaction potential, if it is positive, reaction will be spontaneous. So first half cell plus 2 times second half cell reaction, that is equal to cell reaction. So inert 1 plus inert 2, that gives inert cell. That is the answer. Second question, which cell will measure standard electrode potential of copper electrode? For any potential of an electrode, you need to connect it with SHE, standard hydrogen electrode. Then standard hydrogen electrode characteristic is that the pressure of the hydrogen gas is 1 bar. And the concentration, molarity of the hydrogen ion is 1 molar. Even for the other cell, the another half cell, the concentration of the ion must be 1 molar. And if gases are involved, its pressure must be 1 bar. So look at the conditions. Here the pressure is not 1 bar. Here the concentration is not 1 molar. Here it is 1 bar, 1 molar, 1 molar. Here it is not 1 molar. So the option we guess it is C. Let us see the answer. Yes, it is the option C. A given cell is coupled with standard hydrogen electrode in which concentrations of ions are 1 molar and pressure of hydrogen is 1 bar. Next question, the standard EMF of the cell, zinc, silver. Look at the symbolic representation of this. So we have here the zinc plus 2 getting oxidized. So here I'll show it. This is oxidation and this is reduction. How you position it, this is on the left side, this is on the right side. This convention is very important. So the cell potential is 1.56 volts. If the standard reduction potential of silver electrode is silver half cell is 0.8 volts, the standard oxidation potential of zinc is. You need to do here two manipulations. First, from the cell potential, you have to calculate the half cell potential of the zinc electrode. Then convert that reduction potential into oxidation potential. Idea is, if the reduction potential is with a minus value, the oxidation potential will be the same value with a plus. So now let us see how that is calculated. Yes, the answer is plus 0.76 volts. So look at the formula here. E0 combination is half cell potential of right hand electrode minus half cell potential of left hand electrode. So that is equal to total, this is actually the potential difference between the right hand half cell and the left hand half cell. So the silver is at right, zinc is at left. So the difference gives you 1.56. From that you are going to find standard reduction potential of zinc with a minus. Then if it is oxidation potential, only the sign changes. Come to next question. The reaction in a cell used in watches is, it consists of the cell reaction zinc and silver oxide, moisture, silver, zinc oxide, OH minus. So half cell reactions are recognized here. Half cell reactions are recognized markedly. So that is, the first one is the zinc. Zinc has to undergo oxidation. So you have to take the reverse process here. Then silver oxide is undergoing reduction. Fine. So when you reverse this equation, this will be plus, but the rule, if you make a combination of these two values are called as standard reduction potential values. And when it is standard reduction potential values, take a difference of these two. And when you write the difference, first you have to take the potential of the reducing electrode, then minus the potential of the oxidizing electrode. So let us see the answer. Yes, it is 1.10 volts. So SRP values of the two half cells are given here, this and this. The difference, SRP of the reducing half cell minus SRP of the oxidation. This rule is applicable to all the cases commonly. So that comes to a positive value, that is cell potential. Next question. The EMF of a galvanic cell made of the electrodes, again zinc and iron. Look at the SRP values of these two. SRP values observe ಮಾಡಿ, ಎರಡು minus ಇದೆ. So when it is both minus, you have to be careful about values. One with a lower value has a tendency for reduction. One with a higher minus value has a tendency for oxidation. So when you write the formula, this half cell is taken as reducing and this is taken as oxidizing. And the difference in value will give the cell potential. Let us see. Yes, the SRP value of zinc half cell is lower than that of iron half cell. So oxidation in zinc half cell, as I told you, when you want to use the term anode, the process must be oxidation. Then when you want to use the term cathode, the process must be reduction. So now you take the difference in potential. We call it potential difference between reducing half cell and oxidizing half cell. That gives you the final value 0.35 volts. Next question. The standard reduction potentials of halogens are given here. Family of halogens we have here. For all the halogens, SRP values are given. Just observe the values. For the first one, plus 2.85, plus 1.36, plus 1.06, plus 0.53 volts. The strongest oxidizing and reducing agents. Here you need to arrange them in the decreasing order of the SRP values. As the value of SRP decreases, tendency for reduction decreases, tendency for oxidation increases. And with that idea, now you are going to get fluorine as the easily getting reduced form. So fluorine can easily get reduced to fluoride. So it acts as a more powerful oxidizing agent. So the option fluorine clue anta tagondre, you arrive at the first answer approximately. Then let us see the answer, how it is worked out. Yes, it is answer A, fluorine and iodide. So the trick you are using here is arrive at the answer approximately and you can guess what may be the answer and then confirm it. Higher SRP value means more tendency for reduction, the stronger oxidizing agent, or it is a weaker reducing agent. That comes to fluorine value. Next, lower SRP value, less tendency for reduction. That is, iodine has less tendency for reduction. So that is, its reduced form, the product I minus has more tendency for oxidation. So that acts as a stronger reducing agent. If zinc 2 plus and zinc SRP value minus 0.76, then EMF of the cell, zinc and standard hydrogen electrode. Look at this. The zinc electrode is coupled with SHE. And by convention, the potential, standard potential of the hydrogen electrode is taken as 0.0. It is a starting point. It is by convention, SHE value is, the potential of SHE is 0. And when you make a combination, again, zinc is getting oxidized and hydrogen plus is getting reduced. So you make a difference in their potential of the reducing electrode minus potential of the oxidizing electrode. See the answer? Yes. Inert cell is inert reduction half cell minus inert oxidation half cell. SHE potential minus SRP of zinc, that comes to plus. Calculate the half cell potentials of different half cells. Look at a very interesting question. Zinc half cell potential, standard potential is given, and magnesium half cell, standard potential is given. Now they have represented the reactants for an equation where zinc is in the elemental form, that is in the reduced form. Magnesium is in the oxidized form, that is in Mg+2 form. This is oxidized form. Now you have to predict what happens. Zinc dissolves. To dissolve, zinc has to become Zinc+2. Zinc chloride precipitates, and to form zinc chloride, it has to form Zn+2. Magnesium chloride precipitates. So magnesium chloride aqueous anta irodrinda, it is not precipitate. Next thing, no reaction. So the idea is very simple. Compare the SRP values. The least SRP, least standard reduction potential, means tendency for reduction is very less. Mg to become Mg+2, more tendency of that. The tendency for Mg+2 becoming Mg is less. Then Mg tries to remain as Mg+2 only, and that means zinc remains as zinc. There is no reaction. So let us see the answer. Yes. Mg is more electropositive than zinc. SRP value ಕಮ್ಮಿ ಇದೆ ಅಂದ್ರೆ more electropositive then magnesium prefers to remain in oxidized form. Zinc has to remain as zinc. That is no reaction. Standard electrode potential of tin half cell where stanic is converted into stannous. Idu reduction. Look at this. Then chromium, sorry. It is chromium to Cr plus 3 to Idu reduction. So the values are SRP values. The values are SRP values. The cell potential of these two couples means you have to find the potential difference between these two. Which one would you consider a reducing half cell? Which one will you consider as oxidizing half cell? Look at the SRP values. One with a negative value or a lower value has tendency for oxidation. One with a higher value has a tendency for reduction. So, E value togondu minus of minus this. That comes to the E naught cell, that is cell potential. Yes, look here. E naught cell equals E naught of reduction half cell minus E naught of oxidation half cell. So comparing the values, tin reducing half cell, chromium half cell is oxidizing. You get the answer plus 0.89. The standard electrode potentials of half cell reactions are, you have two half cell reactions given here, eradu reduction, eradu SRP values. Let me write these two. And when both are minus, compare their numerical values. One with a higher negative value has a tendency for oxidation. One with a lower negative value has a tendency for reduction. So you can take the difference in their potential using that formula. E naught cell is E naught reduction half cell minus E naught oxidation half cell. Look at this. E naught reduction half cell is iron. E naught reduction half cell is iron. E naught oxidation half cell is zinc. So the difference gives plus 0.32 volts. On the basis of the following inert values, the strongest oxidizing agent is, look at the two processes given here. You need to concentrate on the iron of the two because iron undergoes change in oxidation number. So the first case is here. So it is FeCN6 4 minus ferrocyanide anta ಹೇಳ್ತೀವಿ. ಇದರಲ್ಲಿ iron, so ಇದರಲ್ಲಿ iron plus 2 ಇರುತ್ತೆ. This is converted into plus 3. What do you call this process? It is oxidation. This is oxidation potential. SOP. SOP. Let me write. Next, ferrous to ferric. This is also oxidation. Idu SOP. Next, what is the idea? When SOP is higher, SOP higher means tendency for oxidation is more. When SOP is lower, tendency for oxidation is less. For the reverse process, tendency for reduction is more. So reduction tendency will be more, means this species can easily get reduced, means that can act as a strong oxidizing agent. Let us see the calculation. Yes, both are SOP, standard oxidation potential values. Lower SOP means the second case, lower tendency for oxidation, higher tendency for reduction in case of the reverse, ferric to ferrous. That means the ferric has strong oxidizing action. The standard electrode potential values of the three species A, B, C and D are given here. So the values are plus 0.68, minus 2.50, minus 0.5. Then you arrange them in an order on their value. So first comes this, next comes this, the third one is this. So that order is the decreasing value of or SRP value, standard reduction potential values, means tendency for reduction decreases in the order. So that is how you arrange them. The order of their reducing power means tendency to reduce decrease ಆದರೆ ಅದರ reducing power ಜಾಸ್ತಿ ಇರುತ್ತೆ. That means it has more tendency for oxidation, that acts as a good reducing agent. So let us see how that is calculated. Yes, lower SRP value means greater is the reducing power. So when you arrange the values, you come in this order, that is B greater than C greater than A. The standard oxidation potential of zinc, copper, silver and nickel are respectively plus 0.76, minus 0.34, minus 0.8 and plus 0.25. So be careful about these values and arrange them. If possible, arrange them in an order in decreasing or increasing. Which of the following cell reactions will provide maximum voltage? The clue is take any two combinations. These two or these two or these two or any two combinations. You work out the difference in potential, but you must be careful about that combination. So E naught cell is equal to E naught reducing tendency minus E naught oxidizing tendency. And when you want to select these two values, look at the values. So one with a higher SRP value comes here, one with a lower SRP value comes here. So like that you work out and you get a combination where the E naught value becomes very high. So that can be taken as a maximum voltage. So look at this. Cell voltage depends upon the difference between the potentials of reducing and oxidizing half cells. Half cell with a lower oxidation potential, what is given is SOP values. Lower oxidation potential has more tendency for reduction. So using the formula, you apply that to all cases, all possible combinations. Then we find among them the highest value will be for this difference. Difference in the potentials of silver electrode, which undergoes reduction, and oxygen electrode, which zinc electrode, which undergoes oxidation. So that is the highest value for a combination, 1.56 volts. Next question. If E naught cell of a reaction has negative value, so normally when you build a cell, we expect the value of that to be positive. Only when the value of that is positive, you get something as profit, something as energy coming out. But if it is a negative value, the process is non-spontaneous. And with that clue, you can guess delta G is not negative. It comes to positive. Positive andre, it will be greater than 0. Then when delta G naught is positive, the forward process is non-spontaneous. The backward process would be spontaneous. And when there is a non-spontaneous process, its equilibrium constant will be very less. Less means fraction. It is less than 0. With this clue, now you arrive at one of the answers. Look at that. Guess it. Yes, the answer is delta G naught. We call it as the Gibbs free energy of the process, greater than 0. That means positive. Then equilibrium constant is less than 1. That is obtained from the very important relationship here, that is delta G naught is minus NF E naught, where N stands for the number of moles of electrons involved here, and F is a Faraday quantity of electricity, and E naught cell is the cell potential. Look at this half cell. The pressure of hydrogen gas in atmosphere required to make the potential of hydrogen electrode 0 in pure water. What is used is pure water at 298 Kelvin. You build a hydrogen electrode where instead of HCl, you are going to take pure water. And what will be the pressure of the gas to be passed to make its potential 0. So here the idea is potential of this electrode must be equal to the standard potential, that is 0, 1 point. Another point is how much will be the concentration of H plus. The hydrogen ion concentration in water, you must know this to calculate this. And what you are going to use here is the famous Nernst equation. So Nernst equation can be used here to solve this. Look at this. Nernst equation for an electrode. Here the electrode involved is hydrogen reduction. Then Nernst equation is E electrode is E naught value, L E naught value minus 0.059 by N log of pressure of hydrogen by molar concentration of hydrogen. ಇದು ಈ equation ಇಂದ ಮಾಡ್ಕೊಂಡಿರ್ತೀವಿ. Where number of moles of electrons involved for reduction, this is number of moles of H plus reduced. Then come to pure water where its pH is 7. From that pH relation, you find the molar concentration of H plus. And when you know all of them, so E value, E naught value 0, number of moles of electrons involved 2, and molar concentration of hydrogen is 10 to minus 7 molar. From that, you are going to find the pressure of hydrogen as 10 to minus 14 atmosphere. So that is, let us see the next slide. Standard potential of Daniell cell is 1.10 volts. The standard gives energy of the cell. You must know what makes a Daniell cell. It's a combination of zinc half cell and copper half cell. Zinc undergoes oxidation, then copper 2+ undergoes reduction. And you make a combination of these two. And when you want to take them in standard state, this must be 1 molar and this must be 1 molar. What is given here is its potential 1.10 volts. So it is positive. So the process is spontaneous. Then you have to find delta G naught value. It is the standard Gibbs energy of the reaction. Here is a relationship which you are going to use. Look here. Yes, the relationship is delta G naught equals minus NF E naught cell. Number of moles of electrons involved in the process. Look at this. Number of moles, and there are 2 mole electrons are involved. Then F Faraday is given. Then E naught cell is also given. You get the value in joules. The answer is in kilojoule divided by 10 to 3. In an electrochemical cell, the reaction will be feasible. What do you mean by the word? It is spontaneous. That means you must have the idea delta G or delta G naught must be minus negative. It must be liberated. Gibbs energy must come out. So with that idea, you find this relationship, you know, delta G and E are related like this. If E is positive, then delta G naught will be negative. So look at that combination in this answer. Let's find out. Yes, delta G negative, E, the potential of the cell is positive. That is on the basis of delta G is minus NF E cell. An electrode is made by dipping platinum wire in a solution of HCl of pH 10. Look at this. It's a hydrogen electrode where the pH of the solution is 10. Hydrogen gas is passed at 1 atmosphere. That is standard. That is standard. Then the oxidation potential of the electrode. Certainly this is not SHE. This will be he. She becomes he here. So now how do you calculate this? First you find the potential of the reduction potential, standard the reduction potential of the cell, half cell. Then you reverse it. It will be the positive value where you get it as oxidation potential. Here we use another form of the Nernst equation. So we are going to use Nernst equation for an half cell. You can apply Nernst equation for a whole cell, galvanic cell. You can also apply Nernst equation for a electrode, that is half cell. Let us see the answer. Look at this. Nernst equation for an electrode or half cell. The reaction, electrode reaction is hydrogen plus getting reduced. Hydrogen plus getting reduced. Next, Nernst equation is this. It is E, the potential is E naught, the standard potential, minus 0.059 by N, logarithm P hydrogen, pressure of hydrogen by concentration of H plus. This equation is referred to this, where N, number of moles of electrons is 1, then molar concentration of H plus we find out from the pH. When pH is 10, concentration of the hydrogen in molarity is 10 to minus 10, power of hydrogen concentration. So now you substitute that standard potential is 0, then you substitute this value, you get minus 0.059 into 10. That comes to minus 0.59. But that one is for the reducing reaction. Reverse the sign. That will be for oxidation. So that is oxidation potential. The potential of hydrogen electrode is 18 millivolts. 18 millivolts. Find hydrogen ion concentration. Again, here you need to use Nernst equation where you substitute for potential 18 millivolts, 18 into 10 to minus 3 volts. So look at this. Nernst equation for the electrode, as usual, we have this repetition. So potential is given here. Potential kotidare, it is 18 into 10 to minus 3 volt. Standard potential is 0 volts. N number of moles is involved. Then you get log value of H plus as this. And to make it, you have to take the anti-log for this. Anti-log for this is roughly anti-log of 0.301. And you are familiar with log 2 is 0.301. Anti-log of this is 2. You must be getting answer around 2, or actually you get this 2.02, but the answers given in the question is 2. That is C option. Next, the standard EMF of a galvanic cell involving 2 mole electrons in its redox reaction is 0.59 volts. The equilibrium constant for the cell reaction is, so look at this. Here what is given is standard EMF, E naught cell kotidare, 2 mole electrons, number of mole, N kotidare. So what is given here is the 2, N and E naught. So what you have to find the equilibrium constant. Here is a very important relationship you have here. So very important relationship is that it is K, the equilibrium constant. How do you get this? It is related to the, let me write. So I'll write this equation, that is, then I'll show you the calculator. E naught cell is equal to 0.059 by N log of K. K is the equilibrium constant and log K is E naught cell into N by 0.059. So E naught cell is given, number of moles of electrons involved is given, then the value is already there. You get 20. But 20 is a log form. So you write the log form in 2 parts, characteristic, mantissa. And when mantissa is 0, it is 1 into. Then when characteristic is 20, you write the antilog value as this 1 into 10 to minus 20. So that gives the answer 10 to minus 20. So look at the next question. E1, E2 and E3 are the EMF of the following galvanic cells respectively. Look at all of them are the same combination, zinc and copper and zinc and copper. but you need to notice their concentrations. 0.1 molar, 1 molar, 1 molar, 1 molar, 1 molar, 0.1. So that makes the difference. And potential of the cell depends on the concentrations of the ions. So here again, we are going to use the Nernst equation for the cell. So Nernst equation for the cell. ಇದರಲ್ಲಿ ಕೊನೆಗೆ equation ಅಲ್ಲಿ ಯಾವುದು ಬರುತ್ತೆ ಅಂದ್ರೆ what you get will be here the ratio of, so the ratio of zinc ion concentration, what is the product zinc ion concentration to the ratio of copper ion. This is the only difference in all the three. And if that is different, the value of E differs. How? Let us see that. Look at that reaction of the cell, zinc plus 2 copper. So look at the Nernst equation for this. But what is important here, the last part of the equation, the ratio of their concentrations. Now, if you calculate that ratio for all the three cases, we find the ratio will have 10 to minus 1, that is 0.1, 1 and 10. And that makes the difference between E cell and E naught cell. What you subtract from E naught cell, first 0.1, then 1, then 10. So that makes the difference between E cell and E naught cell. So first case, you subtract less, E1 is greater than E naught. You subtract 1, that means E2 is same as E naught cell. 1 andre log 1 andre 0, no subtraction here. Then here it is 10, you subtract more. So E3 is less than E naught. The solution of standard nickel half cell is diluted 10 times. Its reduction potential at 298 Kelvin. So as I told you, the potential of a half cell depends on the potential of a half cell. So let me write E naught minus something. This minus something depends on the concentration of the ion. So when the concentration of the ion changes, the difference between these two makes it different. So what you are doing is dilution. That means molar concentration of nickel plus 2 decreases. What you subtract from E naught will be less. The value will be ಎಷ್ಟು ಆಗುತ್ತೆ, ಇದು ಇದಕ್ಕಿಂತ ಎಷ್ಟು ಕಮ್ಮಿ ಆಗುತ್ತೆ, ಮೈನಸ್ ಇರೋದ್ರಿಂದ E naught ಗಿಂತ ಇದು ಎಷ್ಟು ಕಮ್ಮಿ, that is we measure. So now let us go to the answer slide. Yes, decreases by 30 millivolts. So as usual, Nernst equation for the nickel half cell we have written. The Nernst equation for the nickel half cell, this is. So what is important here is, for a solid, it is always constant 1. So that is 1 molar. Then what you do here is the concentration changes from 1 to 10, 10 to minus 1 molar. So this goes to the numerator and becomes 10. So 10 bandaga, it is log 10 is 1. So the value we have to do here is 0.06. Instead of 0.059, I am writing the rough value 0.06. You are allowed to use this value 0.06 in this Nernst equation. So that comes E less than E naught by 3 into 10 to minus 3 volts. That is 3 millivolts. Here is a very important question where it depends on a very important law known as Kohlrausch law. So lambda naught m represents limiting molar conductivity of an electrolyte. It is also called molar conductivity at infinite dilution, which will become constant. Further changes will not take place. So lambda naught m of a electrolyte, ammonium chloride, sodium hydroxide, and NaCl are given. So look at them, they are all salts, they are all strong electrolytes that can be measured experimentally. Then what they require is the lambda naught m of weak electrolyte, that is ammonium hydroxide. Here we make use of the law known as Kohlraasch law. So according to that, if it is a electrolyte AB and if you want its limiting molar conductivity, that is taken as a sum of the molar conductivities of the two ions A plus and B minus. So lambda naught B minus. So the combination of the two ions will make the value of this. So all the three strong electrolytes, they can be split up into their combinations. Required combination of the two ions can be taken and you can get the value like that. So look at that. Lambda naught M of ammonium hydroxide is equal to lambda naught M of the first salt, ammonium chloride, plus lambda naught M of the second salt, sodium hydroxide, minus lambda naught M of this. Yake idu bantu annadu ili toristundi. Idu NHO plus Cl minus, idu Na plus OH minus, idu Na plus Cl minus, idu minus irodrinda Na plus goes, idu Cl minus goes, and what remains here is the two ions OH minus and NH4 plus. That combination will be a electrolyte, ammonium hydroxide. And when you apply this formula for Kohlraasch law, a similar manipulation is done for values also. Formula ಹೇಗಿರುತ್ತೋ ಅಲ್ಲಿ values ಗೂ ಅದೇ mathematical manipulation ಮಾಡಬೇಕು. So that comes to 251.5. So next question. Conductivity of a saturated solution of a sparingly soluble salt AB at 298 Kelvin is 1.85 into 10 to minus 5 Simon per meter. Lambda naught M, again limiting molar conductivity of the same salt is 140 into 10 to minus 4 Simon square meter per mole. Solubility product of the salt. Now you know solubility product, that is actually depends on the solubility. So it is the concentration of A plus, concentration of B minus when the solution is saturated and the reaction, the process has attained equilibrium. So here we relate this KSP to solubility, and the solubility is related to K, that is conductivity and limiting molar conductivity. So this two can be used to find solubility. Solubility can be used to find solubility product. Let us see the actual formula. Yes, solubility is related to conductivity of the solution and limiting molar conductivity, like it's a ratio of conductivity to limiting molar conductivity. And why is this we have used? Look at this, I'll show you. So we convert this K Simon per meter to Simon per centimeter. Limiting molar conductivity, Simon square meter, we convert into Simon per square centimeter. Then we convert that centimeter cube to liter. So the 10 cube there comes because we are converting cc to liter. This is in the formula. So you substitute the values after conversion, you get the value. Yes, solubility is 1.32 into 10 to minus 6. Then for salt AB, we write the solubility for product formula. Solubility product formula is here. K is S into S, S square. That is 1.32 into 10 to minus 6 square. That comes to the final answer, 1.74, 10 to minus 12. At 25 degrees C, the molar conductivity of 0.07007 molar hydrofluoric acid is 150 mho. Idu ohm to the power of minus 1 badlu mho. So that is actually Simon square centimeter per mole. And its limiting molar conductivity is again that mho square centimeter per mole. The dissociation constant of the acid at that concentration and temperature. Here we have an equilibrium where we have the products H plus concentration, F minus concentration when the HF undergoes dissociation. It will not completely dissociate because it is a weak electrolyte. You need to find the ratio, that is equilibrium constant, known as dissociation constant. Then to know this, you require extent of dissociation. To what extent this dissociates into these two ions, and that is called degree of dissociation. This is found out from the two values, molar conductivity and the final value, the limiting molar conductivity. This is molar conductivity, this E ratio. From this you find alpha and from this you find K. Let us see the answer. Look at this. Molar conductivity is lambda naught. It is lambda naught, lambda m. Limiting molar conductivity is lambda naught m, and the dissociation is represented, actually it is dissociation HF plus F minus. First you find the extent of dissociation, how much of HF dissociates. It's directly related to this ratio, and that comes to 0.3. What do you mean by alpha 0.3? If you have taken 1 mole HF, out of that 0.3 mole HF gets converted into H plus and F minus. And then we have equilibrium constant value ಇಲ್ಲಿ ಬರುತ್ತೆ. So that is C alpha square by 1 minus alpha ಇಲ್ಲಿ, where C is the initial concentration of the solution. Then you substitute all of them together. You get this K, the equilibrium constant, 9 into 10 to minus 4. Next question. The specific conductance, you can also use another word for this. Specific conductance can be called as conductivity. Of N by 10 KCl at 25 degrees C is 0.0112 per ohm per centimeter. The resistance of the solution in a conductivity cell was found to be 55 ohm. Resistance is 55 ohm. The cell constant. How are these related? So you write the formula. I'll write this. Conductivity or specific conductance is cell constant, which is a constant for a particular apparatus, conductivity cell, divided by resistance. Idu jasti adashtu idu kammi agatte. So this remains constant. What you need to calculate is this cell constant. So let us see the calculation. Yes. K is equal to G star by R, but we want just cell constant, we want specific conductance into resistance. That comes to 0.616 per centimeter. The quantity of electricity in Faraday required for the reduction of 1 mole dichromate to chromate. I'll give you the clue. So look at this. Cr2O7. In this, the chromium has oxidation number +6. And from 2 chromium, it will be +6 into 2. That comes to +12. Then this side, it is 2Cr3 plus. 2 yak barkobeku andre balance agbeku. You need to balance it. Here, the oxidation number is +3 for chromium. So from 2, it will be 2 into +3. Total oxidation number is +6. Look at the change in oxidation number. It is 6 units. For every unit change in oxidation number, you require quantity of electricity 1 Faraday. And for changing 6 units, 6 unit change it requires 6 mole electron. 6 mole electron is 6 Faraday. For every mole of electron passing, it is 1 Faraday. Let us see the calculation. Yes. Decrease in oxidation number of chromium by 6 units from 12 to 6 due to addition of 6 mole electrons, which amounts to 6 Faraday electricity. How many coulombs of electricity is required for the oxidation of 1 mole water to dioxygen? Whenever a process is given and you need to find the quantity of electricity involved, you have to be careful about first dissociation, then what happens at the anode, then what happens at the cathode. So here it is 1 mole water to dioxygen, we say. So I take 1 mole water, I'll dissociate this. 2H plus and O minus 2. Let me write. First, they are converted into ions. What is given here is dioxygen. O2 matra kelirodrinda. Dioxygen is found by oxide ion. Oxide ion goes to the anode. So what happens at the anode is very important. I told you it is oxidation, loss of electron. When O minus 2 ion loses 2 electrons, it will be converted into half O2, dioxygen gas. What is involved here is 2 mole of electrons. That comes to 2 Faraday. But what is required, the unit is coulomb. You must know the relationship between Faraday and coulomb. 1 Faraday is 96,500 coulombs. Convert finally to coulombs. Let us see the calculation given. Yes, it is dissociation of water at the anode. Oxygen matra togoli. ಇಲ್ಲಿ ಕೇಳಿರೋದು oxygen matra. That is 2 mole electron is important for oxidation. That is 2 times Faraday, 2 times 96,500 coulomb. That is the answer. Again, a similar question. In the electrolysis of acidulated water to get 1.12 cc of hydrogen per second. Look at this. So 1 second is fixed. It is at SGP. They have given the volume of hydrogen at SGP. The electric current, quantity of electricity is different. Electric current is different. I'll write it like this. If Q is the quantity of electricity, it is I into T. It is a product of electric current and time. Time is given as 1 second. You need to find I. You have to first find out this in Faraday or Coulomb. Faraday or Coulomb, you can find out more. So how do we find that? This is found out from amount of the product found, whether it is 1 mole. If it is 1 mole, it is 1 Faraday. Like that, you have to calculate it. Look at this detailed calculation. So dissociation. Hydrogen is given as an important product. So we take what happens at the cathode. Hydrogen plus is reduced to hydrogen. What is involved there is 2 mole electrons. That means 2 Faraday is required. And they have converted the hydrogen, the product, 1 mole hydrogen into volume. This is called gram molar volume. If it is 1 mole hydrogen, it is so many cc. But what is produced here is 1.12 cc. Find out the quantity of electricity for that. So it is for 1.12 cc, the quantity of electricity is 10 to minus 4 Faraday. Then convert that quantity of electricity to electric current. So the electric current I is 9.65 amperes. So that is the answer. Last question, very important, we have come to. For the hydrogen oxygen fuel cell. So the net reaction is given here. The net reaction is hydrogen plus oxygen water, but actually 2-step reaction we have to write. One at the cathode, the other one at the anode. What is given here is the Gibbs energy of that, the outcome or the profit of that in terms of Gibbs energy. So at 298 Kelvin and 1 at. So what they want is the E naught of the cell. So now let us find out this like this. It is a relationship between G naught and E naught. How do you find this? It is delta G naught equals minus N F quantity of electricity into E naught cell. So here what we know is this 96,500 coulomb. ಇದನ್ನ ಕಂಡುಹಿಡಿಯೋದಕ್ಕೆ equation ಹಾಕೋದು. What you have to find, number of moles of electrons involved in the redox process. You have to find this N. So let us see the answer. So look at this. It is delta G naught is Gibbs energy is related to potential of the cell like this. 2 mole electrons are involved. How do you write this? I'll show you. It is, so O2 is oxidized. Let me write it. This is, I'll write it for you. So it is, the two gases are involved here. The two gases, hydrogen and oxygen. What else is used here is the OH minus. Alkali will be used in the cell. It is H2, 2OH minus. It is 2H2O plus 2 mole electron. This is oxidation. Here what it forms, oxygen will react with water. With the electron released from that, it will give, say, 2 OH minus. OH minus is replenished. Then what is involved here in the whole process is 2 moles of electrons. That is why the N is 2. And when you add up these two equations, this is actually half O2. So H2 plus half, H2O plus half O2 gives 2OH minus. Then we add up this, it gives the total reaction H2 half O2 H2O. That is the advantage of the hydrogen oxygen fuel cell, where the product is unharming, that is, it will not cause any pollution. So now you have the inert cell positive, that is 1.24 volts. How much is the voltage or the output of hydrogen oxygen fuel cell means that is 1.24 volts. So that's about this topic.